Today's class, let us learn about basis of a vector space. What do you mean by basis of a vector space? Suppose I have a vector space V over the field F and I have set of vectors, say V1, V2, like that, Vn. I'm saying that this forms a basis for the vector space V if I can write every vector in this set uniquely as a linear combination of rest of the vectors. Means if every V in V, okay, can be written as linear combination of these vectors, and this expression is unique. A1 V1, A2 V2, like that, AN Vn, where each AI is from the field F. Then I can say that this set forms a basis for the vector space V. Means I can say any set, say in general, if I have a set, it's a subset of V, okay, I can say this forms a basis for the vector space V if this set S is linearly independent set and the subspace generated by this S, this S should span the vector space V. Then I can say that S is a basis. This is another way of saying same thing. This linear combination means they should span the vector space V. In the sense, every vector in V can be written like this, and this expression has to be unique. And the thing is, these vectors have to be linearly independent. I remember one thing. If the set of vectors, say V1, V2, like that, Vn, if this is a basis, okay, then the subspace generated by these vectors is a whole vector space itself, okay. Subspace generated by this, in the sense linear span generated by this, is a whole vector space itself. If I have vectors and they are the basis, then, so this is yes, then the subspace generated by this is whole vector space, okay. But the converse part is not true. If I have some set of vectors, they are spanning the vector space V, but I cannot say that that subspace is a basis. If I have, say, set of vectors V1, V2, like that, Vn, they generates vector space, okay, means they span the vector space V. But this need not be basis for V. If it is a basis, then of course they span the vector space. But if they are generating or they are spanning the vector space V, then they need not be a basis for vector space V. For example, suppose I have a vector space V over R3, okay, and suppose I have vectors, say 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, and I'll take say 0, 1, 2, suppose, okay. These are the vectors, okay. They generate the vector space V, okay. They generates R3, vector space R3. Now, I'm saying this need not be a basis for R3 because, see, element 1, 1, okay, is in R3, right? To say this forms a basis, every vector in R3 should be the linear combination of this, and that representation has to be unique, right? So I'll take the vector 1, 1 from R3. I'll write this 1 comma 1 as a linear combination of these vectors. So I'll name these vectors. This is vector v1, v2, v3 and v4. Okay. So this 1 comma 1 that belongs to R3 can be written as v1 plus v2 plus v3. Do you agree? That is 1 comma 0 comma 0 plus 0 comma 1 comma 0 plus 0 comma 0 comma 1. Right, this is one way of writing. If this is the only one way, then I can say that this forms a basis. I mean, when you consider particular element. Okay, but this 1 comma 1 comma 1 can also be written like this. I can take, say, v1. I'll add up with this. V4. I'll subtract this. Okay, minus v3. See, now look at this. v1 is 1 comma 0 comma 0. Okay, v4 is 0 1 2, and I'm subtracting v3 0 comma 0 comma 1. See, 1 0 minus 0, so it is 1. 0 plus 1 minus 0 1. 0 plus 2, 2 minus 1, that is 1. So this 1 comma 1 has got two representations. Therefore, I can say that this, even though the vectors generate vector space V, but they do not form a basis for R3. This is one, if there exists one such element for which you have got more than one representation, then you can say that this do not form a basis. Okay. So the thing is, I can say set of vectors which forms a basis if and only if they are linearly independent. So let us do the proposition. It says, let V be a vector space generated by the vectors v1, v2, dash dash vn. Then these vectors forms a basis if and only if the vectors are linearly independent. So let us take the first part. I'll just take first part as this forms a basis, and I have to prove that these vectors are linearly independent. So the first part, suppose the vectors v1, v2, dash dash vn, they form a basis, is a basis of v. Then I have to show these are linearly independent. Okay, in the sense I have to take a linear combination of vectors equal to 0, and if I end up with all scalars equal to 0, then it means these are linearly independent, right? So to show linearly independent nature of this, let me take their linear combination, say AI, VI equal to 0. All AIs are from the field F. Okay. Now, any 0 vector, okay, can be written as, or any element 0 can be written as 0 into V1 plus 0 into V2, like that, 0 into Vn. Now I know that this expression, since it's a basis, this expression is unique, right? So by the uniqueness of the expression for 0 as a linear combination of this v1, v2, linear combination of these vectors, I can directly say a1 is equal to a2 equal to an, and this they are equal and they are equal to 0 by the uniqueness of the expressions for 0, uniqueness of the expression for this element 0 as a linear combination of is a linear combination of these vectors v1, v2, vn, I can say that a1 is equal to a2, like that they are equal to an, and which is equal to 0. Therefore, I can say that all the vectors vi are linearly independent. First part is over. Vectors, I have taken these vectors form a basis, and I have shown they are linearly independent. The second part is converse part. I am taking these vectors v1, v2, vn are linearly independent set of vectors. I have to show they form a basis. Okay, suppose any vector v, okay, if it can be written like this, I ranging from 1 to n. See, I have to show these vectors form a basis. Okay, in the sense, the vectors of v has a unique representation. Okay, so I'll take two different expression. I'll assume two different expression for the vector, and if I show they are equal, then my thing is over. Then it means that they have got unique expression, therefore they form a basis. Okay, so I'll take a vector from V and I'll assume two different linear combinations for the vector. Okay, say this is one more linear combination for the vector, where remember this AIs and BIs are from the field. Okay, then I can write summation AI minus BI into VI equal to 0. Since they are equal, so I can write it like this: their linear combination is equal to 0. But I know that these VIs are linearly independent, Therefore, what has to be true? Where I ranges from 1 to n. So, I have got coefficients equal, AI equal to BI. Therefore, if I take any vector from V, which can be uniquely expressed like this, therefore, the vectors of V means V1, V2, Vn form a basis. So now let us look at the examples. Suppose first example, suppose I have a vector space V, which is nothing but set of n tuples Rn. And then the vectors say E1, which is also a n tuple 1, 0, 0. Vector E2 is 0, 1, dash dash dash, like that. Nth element is 0, 0 dash 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 1. Then I can say this set E1, E2 dash dash En, they form a basis for vector space Rn. In fact, it is a standard basis for the vector space Rn. If I take say my vector space is complex numbers, C complex space, over the field R, okay, over the field R, then basis is, I'm just mentioning the standard basis, that is 1, I, okay. Because see, you can check, see how is any element in C? This is of the form x plus iy, right? Where x and y, this is complex space over real number. So x and y belongs to R, right? Now, I suppose I want to generate a complex number, say 2 plus 3i. Okay, suppose I want to generate this. Then, see, I'm taking some alpha. I cannot just take one in my basis because element is of the form x plus iy, right? So I'll take alpha into 1 into beta into I. Now I am giving value 2 to alpha and say 1 to 3 to beta. Okay, so that I'm getting 2 plus 3i for alpha and beta. If I give like this, because these are the elements from the field, and here the field is set of real numbers, right? If I take only one, then I can just write something into 1 plus something, maybe multiplied with some other thing. I should get a complex number of this form, right? But if I have only one element in my basis, that is 1, then I won't get this term, right? Therefore, I have to add I. This is the standard basis for the complex number over complex space over real numbers. One more example, suppose I want to find the basis of, say, r square over r. Standard basis for this is, you can easily say, how is any element in R2? I mentioned r square, I'm sorry, it should be R2. Okay, elements are set of ordered pairs, x comma y. Elements are in this form, right, where each x and y belongs to real numbers. Okay, so I have to generate this space. Okay, so that set is nothing but the basis. If I take one vector, that is 1 comma 0 and e2 is 0 comma 1, then from this set of vectors I can get the vectors or two tuples in R2. All the vectors in R2 can be written in the linear combination of these two vectors. So I can say this is a standard basis for R2. Other than this, I may have some other basis. I can say the vector, say 1 comma 1 and another vector, say minus 1 comma 2. Okay, now these two vectors are linearly independent. You can just guess these two are linearly independent, and of course they form a basis. This is not the standard one. These two vectors are linearly independent and they form a basis for R2. You can always cross check. Okay, and one more, last but not the least, suppose I have to find the basis for set of real numbers over Q. Okay, I want to find the basis for R over Q. Now, see, first thing, I'll add 1 to my basis set. This is my basis set, suppose. I'll add 1. Now, R is defined over Q, right? I should get all the real numbers and say something alpha into something along with, say, beta into something. I should get the real number which belongs to R, right? Now, suppose I want to have the number, say, root 2. I cannot write root 2 as alpha into 1. Means if I have to get the value for alpha, that should be from Q, from the field Q, right? Now, if I put alpha as root 2, then that does not belongs to Q, right? So, this is not enough if I have 1 in my basis. To get root 2, the only way is I have to put value root 2 to alpha. But that is not possible because alpha is from Q. Therefore, I should add root 2 to my basis set. Similarly, to get root 3, I cannot put value alpha value as root 3 because alpha belongs to Q. So, I should add that also. It's in fact all irrational numbers getting is not so easy. I can't put the values for irrational values for alpha and beta, right? So this basis for R over Q is an infinite dimensional basis. Okay. In previous examples, suppose here, if I say this is the basis, then only 2 vectors are there. So dimension of the basis is 2. Even here, I am taking the standard basis. Here dimension of a basis means number of elements in the basis set. Here it is 2. Okay, here I have n vectors. Therefore, dimension of the basis is n. Okay. Now let us look at one more term, that is minimal generating set. Suppose I have a generating set, okay, set of vectors v1, v2 like that, vm is a generating set of v. No proper subset of this set generates v, then I can call this as a minimal generating set. Okay, no proper subset. These are the set of vectors which are generating a vector space v. Okay, no proper subset of this set is generating v, then I can call this set of vectors as minimal generating set. In fact, this minimal generating set itself is a basis. So its a theorem states this set of vectors v1, v2, vm is a minimal generating set for v if and only if it is a basis of v. Okay, let us prove this theorem. Let us take first part. Say this set of vectors is a minimal generating set. Suppose vectors v1, v2, vm is a minimal generating set. Okay, suppose it's a minimal generating set for the vector space say v. And suppose if these vectors are linearly dependent. What I have to show is, if this is a minimal generating set, then I have to show it is a basis for v. Okay, to show it is a basis, I have to show these vectors are linearly independent. So I'll just take that, the contradiction part, I'll take this as a linearly dependent set and I'll get the contradiction, so that it has to be linearly independent and therefore it is a basis. Okay, so let me take these set of vectors. Suppose if these set of vectors are linearly dependent, okay, then by the definition there exists a non-trivial solution. There exists a non-trivial solution or relation between the vectors such that summation ai vi equal to 0 where I ranges from 1 to m with some ai's are not equal to 0. Maybe one or more than one coefficients are not equal to 0. So let me take, say suppose a1 is not equal to 0. Suppose a1 is not equal to 0. Then I can write this as a1 v1 plus I equal to 2m ai vi equal to 0. Okay, then this is same as writing summation ai vi equal to minus a1 v1. This is same as writing v1 equal to minus of a1 inverse into summation ai vi where I ranging from 2 to n. Okay, that implies, see, when I write this one vector in terms of linear combination of other vectors, then what does it imply? It implies that v1 belongs to the subspace formed by the vectors v2 to vn. This implies that this vector v1 belongs to the subspace generated by the vectors v2, v3 like that, vm. Right, which implies, what does it imply? This vector belongs to this. Means this vector can be written as linear combination of these vectors. That means this is the generating set for the vector space V, but which is a contradiction to the fact that v1 comma v2 dash dash, this is the minimal generating set for V. Okay, so no proper subset of this generates V. When I take this, when I assume these vectors as linearly dependent, I am ending up with saying that this one vector can be written as a linear combination of these set of vectors. That means this forms a generating set for V, but which is a contradiction. Therefore, these vectors are linearly independent. I'll just write it down. If v1 belongs to the subspace generated by this, then this set of vectors v2 comma v3 dash dash vm is a generating set for V, which is the contradiction which is the contradiction to the fact that we have taken the vectors v1, v2, vm is a minimal generating set. Since it's a minimal generating set, no proper subset of this can generate V. Okay, so thus my assumption is wrong. Thus v1 comma v2 dash dash vm, I have assumed that these set of vectors are linearly dependent. So this assumption is wrong. Therefore, this set of vectors are linearly independent. Okay, since they generate vector V, they form a basis. Since they generate vector space V, they form a basis for V. for the vector space. Okay, first part is over now. I have taken the minimal generating set and I have proved they form a basis. Now second part is converse part. I'm taking set of vectors that they form a basis and I have to show that set as a minimal generating set. Conversely, let the set of vectors v1, v2, vn be a basis for the vector space V. Okay, and I'll take set of vectors v1, v2, vn. This set is not it's a generating set, but I'm taking it as not a minimal generating set. Okay, it's a generating set which is not minimal. Okay, it's a generating set which is not minimal. Then if I say that it is not a minimal generating set, it implies that there is some vector vi which can be expressed as the linear combination of remaining vj's in this set. Okay, which implies there exists some vi which can be expressed as linear combination of remaining vj's. Remaining, just to denote, I'm taking vi vj. Okay, that means say say suppose this nth vector. If I say this is not a minimal generating set, then any one vector in this set can be written as, say suppose this vector, which can be written as a linear combination of this vector. Okay, here I'm just, for the convenience, I'm just taking vn. Okay, this vn can be written as the linear combination of this remaining vectors. Say vn, this can be written as linear combination of remaining n minus 1 vectors. Okay, now this is same as writing a1 v1 plus a2 v2 dash dash an minus 1 vn minus 1 minus or plus minus 1 into vn, which is equal to 0. What is this? This is the linear combination of vectors, n vectors, but here one coefficient is not equal to 0. It means it's a non-trivial relation between the AIs, right? So, which is a non-trivial relation between AIs. So, which contradicts the fact that the assumption which we have made, vectors v1, v2, vn are linearly independent. I have taken these vectors, they form a basis. It means they are linearly independent, right? But when I'm getting this non-trivial relation where one AI is not equal to 0, that means that these vectors are linearly dependent, right? So our assumption is wrong. So this set has to be minimal generating set. Okay, I'll just write it down. I'm getting a non-trivial relation between AI which contradicts the fact that v1, v2 dash dash vn are linearly independent, right? because I have assumed that, I have taken that they form a basis, therefore they have to be linearly independent. Okay, therefore this set has to be minimal generating set. Therefore V1, V2, Vn is a minimal generating set. Hence the proof.